everybody. Thank you for getting up nice and early for this lecture on this nice foggy Manchester morning. So I'm going to talk to you about a different topic today, okay, which is the Bernoulli equation, all right? This is something new. So in the previous lecture, we introduced some key concepts about buoyancy. So it originates from a difference in pressure acting on the upper and the lower surfaces of a submerged object. The buoyancy force is equal to the weight of the fluid displaced. Then we went into the Archimedes principle, which is basically what buoyancy is. And we also considered specific gravity. But at the end, I left you with a slightly tricky question. Okay, so I asked you to think about a balloon submerged in water. Initially, that balloon, okay, is not moving and it's in equilibrium, which means that the weight down is balanced by the buoyancy force upwards. But then I said, okay, what happens if I move the balloon down just a tiny bit? Okay. Well, let's think about the physics, okay? You have to work through the physics in this particular problem to understand it. So when you pull the balloon down a bit, what happens to the pressure?
The pressure increases.
Yes, so the pressure increases. So what happens to the gas inside the balloon when it's subject to a greater pressure? Anybody? A smaller balloon, thank you. Okay, so it compresses a bit. So therefore, if the balloon has compressed a bit under the increased pressure, okay, the volume has reduced. Therefore, what happens to the buoyancy force? It reduces, exactly. And so when it reduces, that means your system is no longer in equilibrium. Whoops. It's no longer in equilibrium, so the balloon will go down. Okay, so just by moving the balloon down a tiny bit from its equilibrium, it then shoots down because we've changed the pressure, we've changed the volume. Hence, we've changed the weight of water displaced and the buoyancy force. All right, so the objectives of today's lecture are we're going to consider the mechanical energy of a fluid. We're going to learn about the Bernoulli equation. And we're going to learn about how pressure and velocity vary with each other inside a flow. And then we're going to, very briefly at the end, learn how to apply the Bernoulli equation to some very, very simple fluid problems, okay? All right, so that's what we're going to go through today. So let's just remember about energy, okay? So you will have been taught, probably hopefully in high school, okay, that you have potential energy and you have kinetic energy, and that's constant, okay? So those two exchange between them. So for example, we have the roller coaster just here, okay? And this idea of transferring energy from kinetic energy to potential energy is what allows the vehicle to go along the track. But what about a fluid? Okay? A fluid isn't a rigid object. This car on this track is a rigid object, okay? But fluid isn't. Fluid moves all over the place. So what happens there? Well, let's consider now conservation of energy for a fluid. And let's just consider the water being forced out of this fire hose here by this firefighter. Now, one of the things you'll notice, okay, is that this firefighter here is stationary. He's absolutely static, but the water is coming out of that hose at a very, very high velocity. So, question number 1. How do we obtain such high velocity and a high kinetic energy for the fluid? Well, you probably realize from playing with bath water and everything else when you're a kid, or some kind of water toy, okay, using high pressure. We put the water under high pressure and boom, out it comes out of the hose. But now we've got another question, slightly more awkward now. How is pressure related to energy? Okay, we've just said, I get high kinetic energy fluid, high velocity, by putting it under high pressure and releasing it through a hose. But how is pressure related to energy? So that's a question we're now going to consider. Now, before, you've probably been used to thinking about your two forms of mechanical energy, which is kinetic energy and potential energy. And you've probably been looking at these two, okay, which are your standard units of joules of a half mv squared and mgz for potential energy. As engineers, you will get used to thinking more in terms of energy per unit mass, right? Joules per kilogram. So that's a half v squared and gz. So that's the kinetic energy and the potential energy. But I said, what about the energy due to pressure? Well, we're going to answer this question by considering, okay, the work done by a pressure P as it moves this volume of fluid, okay, here, this massive fluid here, under pressure P, into this control volume on the right-hand side. Okay, so we're going to consider what happens when we do that. All right, so we're going to push that fluid into this control volume. We're going to work out the energy that's required to do that. All right, so let's think about the work or the energy, because work done is equivalent to energy, in order to push that massive fluid into our control volume. Work done is force times distance. Okay, so here's force times distance just here. So work done is equal to force times distance. The force acting on this area here is pressure times area. Okay, so we just put pressure times area times the distance moved by the mass as it goes into our control volume. So we're going to consider the work done per unit mass. So this is the work done over the mass of fluid. So the work done, of course, is this pressure times area times distance. And the mass of fluid in this little volume here, okay, is rho times the area times the distance d. Now you can see that A and D will cancel, and we're left with P upon rho. So we have this nice P upon rho, pressure upon density. And this is what we call the flow energy. All right? So this is what we call the flow energy. P upon rho is the work required to push a unit mass into or out of that control volume. So we're beginning to answer this question: how is pressure related to energy? So now we've got the flow energy in addition to the kinetic energy and the potential energy. So here is our little table, okay? So we've got flow energy due to pressure, and then here is flow energy due to pressure per unit mass, okay? So there's no mass there. So engineers nearly always work with these quantities, and then right at the end of our calculation, we then multiply it by the mass or the mass flow rate in order to work out the exact quantity we need for our design or our analysis. So I advise that you sort of get used to this concept of using per unit mass on the right. It's generally easier. Okay, So if we now sum all of those terms together, okay, you can see we've got P upon rho plus a half V squared plus GZ. So for steady, incompressible flow, the sum of these energies is constant. Okay, so that's conservation of energy, so it's constant. So there we've got P upon rho, so there's the flow energy, P upon rho. There's the kinetic energy, a half V squared. And then here is the potential energy. And those terms are all constant. So you're going to grow to know and love this equation because it will help you solve so many problems. It will help you think about so much physics and so much engineering that you see around you. Okay, so really familiarize yourself with this equation. So this was first stated by Bernoulli back in 1738, and as I've just said, it's a very, very powerful tool in fluid mechanics analysis. Now, strictly speaking, all right, the Bernoulli equation should be stated as the sum of the kinetic potential and flow energies of a fluid is constant along a streamline. So that's key point number one. Okay, so here's the streamline here. Okay, so it's constant there. It must be in a steady flow. All right, so here's my steady flow, where the frictional and compressibility effects are negligible. You will look at compressibility later in sort of years 2 and 3, okay? But for now, this is how it should be considered. So I can say between points 1 and 2, so here's point 1, here's point 2, and I have P1 upon rho plus V1 squared upon 2 plus GZ1 is equal to P2 upon rho plus V2 squared upon 2 plus GZ2. It's constant along the streamline for incompressible and steady flow. Now, that was a bit of a hand-wavy derivation. Okay? I don't like hand-wavy derivations. They're useful for physical insight, but really, I like to understand things at a very fundamental level. It's only by understanding things at a fundamental level that you really understand how to apply them in practice. Okay? So we're going to go through a much more rigorous derivation now. So what we're going to do is we're going to consider the forces acting on a small fluid element. So here is my fluid element here, okay? And it's moving along this streamline S. And it's got a cross-sectional area A, okay? And it's moving with velocity V. And you can see I've got several forces acting on this fluid element. So we're going to apply Newton's second law, which for this context is F is equal to ma. So please note that F is equal to ma is not Newton's second law. It's a consequence of Newton's second law. So along the streamline, we have a force acting here, P times A. We have a force acting at the other end, so P plus an extra little dP times A. And then we have the mass of our element itself. All right, so we can cancel a few terms. You can see we can cancel the p's there. And this simplifies to minus dP times A minus mg cos theta is equal to ma. The mass of the fluid element must be equal to the density times the volume. So that's rho times A ds. So we can substitute that in. And we're beginning to make progress now with our equation. And if we cancel the A's, okay, so we've got 3 areas in there, and if we cancel those areas, we're left with this equation at the bottom. So minus d of p upon rho minus dsg cos theta a ds. So far, so good. We now have to deal with this term on the bottom right, this a ds. Some of you may know how to deal with this term already. Some of you may not. So we'll just have a quick look at that now. So we're making a bit of progress. This is a much more fundamental approach to understanding what's going on. So let's just think about the geometry and this ADS term, okay? So first of all, I've got this distance ds along my fluid element. Well, I've got an angle there, theta, all right? And so that's my distance there, dz. So I can just use a quick bit of trigonometry and say, well, ds cos theta must be equal to dz. So that's going to simplify that term for me. And then from mechanics, we actually know that v dv is equal to a ds. You can prove this to yourself just by manipulating dv dt and ds dt, and you end up with this. It's a very useful substitution. So that means we can now substitute that and those terms into our equation, so it then becomes this nice, elegant, clean equation. Okay, so we have minus dp upon rho minus g dz is equal to v dv. So those two terms are coming from those ones just there. So we do a bit of rearranging. We put everything on the right-hand side because then it looks nice and neat and tidy. We can now integrate this equation between points 1 and 2. So where are points 1 and 2? They're at either end of my streamline, okay? So here's point 1, and then here is point 2, just here. So I'm going to integrate this equation between points 1 and 2. So here is my integral. You can see down here, I've got between, here's point 1, here's point 2. I'm just going to integrate the whole thing. And when I do, I end up with the same equation that I stated to you before, except that now I've done it in a mathematically rigorous way that takes into account the physics properly. So, yes?
What is the variable that we should integrate this to? Because integration is usually integers with respect to a single variable, right?
Correct. I split this integral into 3. 1, 2, 3. 3 separate integrals. I integrate together. I will get this.
Oh, you separate each integral into a separate one with respect to variables that is different.
Correct. Correct. Okay. Now, more generally, if I don't integrate between points 1 and 2, I can say, well, my p upon rho plus a half v squared plus gz is equal to constant, which is exactly what we said at the beginning. So, in fact, to obtain this equation, we made some implicit assumptions, okay? So first of all, we assumed we had steady flow. Okay, that means it does not change with time. So steady flow means no change with time. Secondly, we assumed it was incompressible. So that means that the density remains unchanged. We're considering flow along a streamline, but any flow is composed of an infinite number of streamlines. We didn't consider friction at all. We didn't consider any work, as in pumps or turbines, taking work out of the system or putting energy into the system. And we didn't consider any heat transfer. So 6 assumptions were supported in this derivation. When you derive something, it's always important that you know the assumptions, because then you know the limitations of how to apply that bit of physics or that bit of maths in an engineering context. We'll come back to these later. Particularly frictionless flow. That's quite a big assumption, because you know there's friction in almost everything. So, what are some examples of situations where frictional effects may be significant? Well, here you've got the example of flow past a sudden sideways expansion. You can see this corner just here, or that corner just there. And as the flow goes past that corner, there's a very sudden pressure drop, and it's equivalent to a friction. Suddenly what's going on at the wall is important. Another example on the right-hand side is what happens when you've got this very long, narrow tube, and the flow is going along it, and it's eventually, on a very, very long tube, the friction effects begin to become important. In 2 or 3 lectures' time, we'll look at flow inside a pipe with friction. Then you've got another example down here on the bottom left. Okay, so you've got flow through a valve, and you can see actually this is quite a complex geometry, and the flow as it goes through the gap here is changing quite a lot. And then finally, in the bottom right, we've got this case of flow near a solid wall. Okay, and you've got the flow as it's going past, and there is some friction effect there, and sometimes it can be important depending upon the surface. So if you've got something that's a very smooth surface, you can basically neglect friction. Sorry. But if it's a lot of indentations and that sort of thing, then near solid walls it becomes important. Okay, so for these situations, Bernoulli is not valid. All right, so we're going to do a piazza pole. I want you to consider these 2 situations. So you've got flow in 2 converging channels. Okay, in the left-hand example, you've got flow through this sudden constriction. Okay, so sudden constriction. And then here, you've got flow in a nice gradually varying constriction. So the question is, can you apply Bernoulli to A only, so that's the left one only, B only on the right-hand side, both of them, or neither? Okay, so which one? So the piazza pole should be open. So if I get this right, aha, there we go. Okay, so some of you think you can apply it to neither of it, which means that that Bernoulli equation we've just been deriving is useless. Okay, some of you think, well, actually I can apply it to both, but most of you think you can apply it to just the right-hand example. So that's this case with the slowly varying geometry. All right, okay. I'm very happy with that. I'm very, very happy because it is correct, okay? So you can only apply Bernoulli to this case on the right-hand side. Why? Why is that the case? Well, if we look at the streamlines for the case on the right-hand side, you can see they're going to be nice and gradually varied. We can ignore any geometrical sort of constriction effects and the friction that then happens because of that. But in the case of A, it's very clear that we're going to get friction losses here at this corner, and this is going to induce a phenomenon called flow separation. And we will come back to flow separation later. It's one of my favorite things in fluid mechanics, is the study of flow separation. So if you chose just B, that's very good. All right, well done. Right, so we're going to do a worked example now, just so that you can start to see how to apply the Bernoulli equation. So a water pipe bursts as a result of freezing, and the water shoots up into the air, reaching a height of 22 meters. The question says, determine the gauge pressure of water in the pipe. So here is my pipe at the bottom here, and then here is the water flowing in, and it's under pressure P. Here is the sudden hole in the side of that pipe, and then here is the fluid going straight up into the air. And the question says, determine the gauge pressure. Now, there are probably multiple ways that you can solve this problem, but because we're in a Bernoulli lecture, we're going to use the Bernoulli equation. So, the first thing we ask ourselves is, what about those assumptions? Do the assumptions allow us to use the Bernoulli equation? So, from the burst point up to the finish point here, the flow is steady, the flow is frictionless, and it is incompressible. So basically, tick, yes, I can start to use the Bernoulli equation. So let's start to set up the problem. We're going to say that our Z location, because we're going to have to consider the height here, the Z location, Z is equal to 0, okay, at where the point where the pipe bursts. That's point 1. Okay, and we're going to consider flow between point 1 and 2. So at point 1, okay, basically the velocity there is 0. Okay, we can safely assume that the velocity is 0 in comparison to the very, very fast velocity that's coming out of the pipe just here due to the high pressure. The value of Z is equal to 1, but we don't know what the pressure is. Okay? At the top of the jet, we know that the water has come to a stop. Okay? So the velocity there, V2, is also equal to 0. Okay? But the height now is 22 meters, which is given in the question, and by definition, okay, the water is now in the air, it's a spray. Okay? So the pressure is at atmospheric pressure. So we've basically got all of the information that we need to do the question. So now we're going to apply the Bernoulli equation between points 1 and 2. So I write out my Bernoulli equation, P1 over rho 1 plus a half V1 squared plus GZ1 is equal to P2 upon rho plus half V2 squared plus GZ2. I now put in the values I've identified above, and my equation simplifies rather nicely to P1 upon rho must be equal to P atmosphere upon rho plus GZ2. Now, gauge pressure, okay, is the pressure above atmospheric. Okay, so then the question asks for the gauge pressure. So that means it's the pressure at point 1 minus the atmospheric pressure. And after doing some rearranging here, we can see that's equal to rho times G times Z2. So we put in our values, and we get 215 kilopascals. So that means that the pressure inside the pipe must be at least 216 or 215 kilopascals above atmospheric pressure in order to shoot that jet of water up to 22 meters. Have any of you been to Geneva? Yes. What's in Geneva? What's very famous in Geneva?
Juggling.
Juggling? I've never seen juggling in Geneva, but you never know. Maybe I went to the wrong place. Yes. CERN, yeah. One of the best places for science on the planet. Yes, over there. Exactly. Okay, there is a massive water jet in Geneva. It goes about 50 meters high. Okay? So with this question, you can begin to think about how pressure is required to shoot that jet of water at 50 meters high. It's very, very impressive. All right? So that's just for you to think about. So let's now think about the mechanical energy of fluid at rest. Okay, this is a useful concept in many different examples and problems. So we're going to consider a large reservoir of fluid, okay, of depth h, and it's open to the atmosphere. So the pressure here, okay, this is atmospheric pressure. It's hydrostatic, which means it is stationary, and so all the velocities in my tank are equal to 0. So at the free surface, so that's at point 1, okay, my pressure is equal to atmospheric. Okay? And that means that my flow energy plus my potential energy, there's no kinetic energy, is equal to P1 upon rho plus GZ1, which is equal to P atmosphere upon rho plus GH. If I look at point 2 now, at the bottom, I can say, well, the pressure at point 2 must be atmospheric plus the pressure due to the height of water h above that point. So that must pressure atmospheric plus rho GH. So my flow energy plus my potential energy is equal to P2 upon rho plus GZ2. I substitute in my values, and I end up with P atmosphere plus, where's my mouse? P atmosphere over rho plus GH. Okay, so these two are the same. So the mechanical energy of the fluid at rest at all points is the same, which is a very useful thing to be able to use sometimes in your analysis, okay? So this just is confirming to us that P1 upon rho plus GZ1 is equal to P2 upon rho plus GZ2. So this is the mechanical energy of a fluid at rest. So that means that the sum of the flow energy and the potential energy is the same everywhere in a hydrostatic tank. So why have we analyzed this particular case? So sometimes when you are looking at a problem and you have a tank that can be assumed or considered to be hydrostatic, sometimes it's much easier to measure the properties at the surface than it is to stick a probe in somewhere in the tank and try to measure the pressure and measure the velocity and all that sort of stuff. So you can start to take this information and make use of it where you can't measure it. Okay, so it's very useful. Right, so here's another very quick example. So we have a large tank which is open to the atmosphere and it's filled with water to a height of 5 meters. There's a tap at the bottom of the tank and it's now opened. And the water flows out from the outlet, okay, from the tap. And the question says, determine the water velocity at the outlet. There's a hint in the question, okay, it says, okay, hint, apply the Bernoulli equation between points 1 and 2. You'll see I've also highlighted there's a point 3 here. We'll mention that in a second. Okay, so in this particular case, okay, we can assume the flow is steady, we can assume it's frictionless, and we can assume it's incompressible. So again, we can use the Bernoulli equation. We're going to put our reference point for our height, z, at the level of the tap because that makes our analysis easy. So at point 1, which is at the surface, okay, the velocity is basically 0. The height, z1, is equal to 5 meters, and the pressure is atmospheric. But then as the water comes out of here, this tap, it just falls out. Okay, well, z2 is equal to 0, and the pressure is also atmospheric. So we put these terms into our Bernoulli equation. So P1 and P2, they cancel because they are the same. V1 is equal to 0. And so, and GZ2, sorry, is equal to 0. And that leaves us with this very simple equation, GZ1 is equal to half V2 squared. We rearrange it and we get V2 is equal to square root of 2 times G times Z1. Okay? So this is a very famous equation derived centuries ago, okay, by a guy called Torricelli. And it's been used by engineers ever since. Okay, so when we put in our numbers, we can see that the velocity comes out at night, the fluid comes out with a velocity of 9.9 meters per second. Now, I said note point 3. Note point 3. We could have just applied Bernoulli from point 1 to point 3, which is what we did with the hydrostatic tank in the previous page, and then applied Bernoulli from point 3 to point 2 in this way. We would have got the same result. Okay? I leave it to you to go and prove it to yourselves at home. A nice little exercise to see if you're understanding Bernoulli. But we could have done the same thing. We could have used that information that we just had. So, what are the physical meanings of each of these terms? Okay, so we've got these terms, but what do they actually mean? So now you can see this is the Bernoulli equation, but in a slightly different form. Okay, we've just multiplied everything by rho, because now we can say, well, this first term, P, what is it? What is P? You say, oh, it's pressure. But I'm going to say to you, what type of pressure? So this is called the static pressure. And that means it's the pressure that the fluid has just by existing. Okay, it's not doing anything. It's not moving. Okay, it's not dropping from a great height. It's the pressure that the fluid has just by existing at that state. Then we have this pressure, the dynamic pressure, okay, of a half rho v squared. So when you're standing on the Manchester street waiting for a bus and you're being buffeted by the wind, okay, that's the dynamic pressure hitting you. Okay, that's what you're feeling, is the dynamic pressure of the wind. And then this one, of course, is the hydrostatic pressure. So this can confuse people because you say, oh, I've got static pressure on the left and hydrostatic pressure on the right. So it's important to understand the distinction between those two. Okay. So hydrostatic pressure really is not a pressure in a real sense, because its value depends upon where you put your Z is equal to 0 position. Because you could say, if I put my Z point here, I've got 0 hydrostatic pressure there. How can that be right? Okay. So you get a hydrostatic pressure difference, and that's what creates the pressure effect. So basically, the hydrostatic pressure accounts for elevation. Now you can see that we have different forms of the Bernoulli equation. All right, so we started off at the beginning of the lecture with energies per unit mass. P upon rho plus a half v squared plus gz. And I said that this first term here, this is the flow energy, P upon rho. We can also express it in terms of just pressures, directly pressures. So P plus a half rho v squared plus rho gz. But we also, engineers, particularly those who are dealing with power stations and hydroelectric power stations, we talk about the height of the water, or the head. Okay, so it's the height of the water. So if an engineer comes to you and says, okay, the head of this water is 100 meters, you've got a physical interpretation already of just how large a pressure that is. All of these are the same, okay, so they're all representing more or less the same physical concepts and idea. Okay, this is the static pressure or the flow energy. So this is the static pressure that the fluid has just by existing. This is the dynamic pressure or the kinetic energy. Okay, and then this is the hydrostatic pressure. So all of these terms, okay, they have the same meaning in slightly different contexts. So it's important that you understand the different forms of these equations, but it's the same equation, okay? All right. So the final thing we're going to think about now is what happens in terms of that relationship between pressure and velocity. That's where we started off right at the beginning of the lecture. So I'm going to consider what happens to flow in a pipe, okay, as the cross-section of that pipe changes. So at the beginning of the pipe, I've got pressure 1, area 1, velocity V1, but at the end of the pipe, it's a bit smaller, the area A2, we've got velocity V2, and the pressure P2. We have incompressible flow, and mass is conserved. So that means that the flow rate of mass at point 1 must equal the flow rate of mass at point 2. So that means that rho times A times V1, that's my mass flow rate in, must equal my mass flow rate out, so rho times A2 times V2. I can rearrange that equation to get an expression for my velocity at the outlet, V2. So if my area changes along the pipe, which it does in this particular example, then my velocity changes as well. Okay, so I've got rho A1 V1 over rho A2. So that means that if my area decreases, my velocity increases. Okay? It must do that in order to conserve the mass. We can't destroy the mass in our pipe. It's not possible. Okay. But don't forget Bernoulli's equation. Okay, so if we consider the streamline along the center of the pipe, we know that the pressure plus a half rho V squared must be equal to a constant. There's no difference in the Z. So this allows us to work out what's going on along our pipe, okay? So you can see that as we go along the pipe and the area decreases, okay, the velocity suddenly increases to a higher velocity. But in order to account for that, the pressure must decrease, okay? So this is very useful because we can use it to create measuring devices. And we're going to have a look at that later in the course. But it's just a very useful concept of understanding the flow as it goes through different types of geometries. So, in this lecture, the key concepts that we have covered have been the different forms of energy in the fluid. We derive the Bernoulli equation for a steady, incompressible, frictionless flow along the streamline. We apply the Bernoulli equation to simple problems. And then right at the very end, we consider the relationship between pressure and velocity. Now, I have one final question for you, just for you to think about over the weekend. So here we've got a glass manometer, all right? And it has oil as the working fluid. And we have airflow in the ductors here. So I've got two questions for you. Will the oil in the manometer here, will it move like this, so that it's lower on the left, higher on the right? Or will it move like this, so that it's higher on the left and lower on the right? And then, what would happen if you change the flow direction? What would the fluid in that manometer do? Okay, so that's the question for you to think about. So at this point, I'd like to thank everybody who's wearing a mask. We do appreciate it. And I will see you next week.